Hello and welcome to Mathematics with Simon. I'm Simon and this is Chewbacca's back. This is the back of Chewbacca. I never want to see the back of Chewbacca. Anyway, you might see the front of Chewbacca at some point. Today we're going to discuss number bases. This is interesting in its own right, and it's also helpful because it lets us know about the inner workings of computers. So our system of number bases is a great invention. We have different digits that represent different numbers, 1, 2, 3, 4, we go up, and then when we get to 9, we recycle the digit for 1, and we put it in a new column, and we call that 10. So this, we have a 9 in the tens column, so that's worth 90, and then a 1 in the units column, so this is worth 91, 92, 93, 94, keep on going up. We get a 9 in the tens column and a 9 in the units column. This is 99, and then we go over to 100. A 1 in the next column over is worth 100. So why is our number system so brilliant? It's brilliant because it allows us to represent any number, however large that might be. It also allows us to represent any number, however small. We can add two numbers easily. We can multiply, subtract, and also divide. So here's 999,999. We go one number bigger, and we get to 1,000,000. So we put a 1 in the next column over, and that is 1,000,000. 1,000,001. This is 0.1, so this is 1/10, 100th, 1,000th, a 10,000th, 100,000th. This is a millionth. So the number system is brilliant, really, because it allows us to represent all of these tiny numbers, as small as we need, and all of the large numbers. Addition. So we've got a method of adding numbers. So 533 plus 196. We don't have to remember this. We don't have to know what this is. We just have to know that 3 plus 6 is 9, so we add down. 3 plus 9 is 12, so we've got 2. Carry the 1. And then 1 plus 1 plus 5 gives us 7. 729. So we just need to know this addition table, which tells us how to add every pair of digits. We can also multiply numbers, so 35 times 42. We need to know that 2 times 5 is 10, so it's 0, carry the 1. 2 times 3 is 6, plus the 1 makes 7. So that gives us 70. That's 2 times 35 gives us 70. And now we're going to look at the 4 that's in the tens column. So we put in a 0 because the 4's in the tens column. Then we say 4 times 5 is 20, so that's 0, carry 2. 4 times 3 is 12, added to the 2 is 14. So we've got 1400 plus 70. 1470. So again, all we need to learn is the multiplication table, which tells us what we get when we multiply together every pair of digits. So we have 10 characters or 10 digits. What if we had 8? So we'd have to go 0, 1, 2, 3. We get up to 7, and then we've run out of digits, so then we'd have to go 1, 0 for 8. 9. This, we've got a 7 in the 8s column, so that's worth 56. And then we've got a 6 in the units column, so this would represent 62. So if we write this in base 8, that's the same as 62 in base 10. 63. So this is 64. So we've got a 1 in that column, the third column across, and that is worth 64. 65. But what if we just had 2 characters? And actually, this is very relevant to computers because if you have a computer, basically you can have either the current turned on or off. On is worth 1 and off is worth 0. So basically then you've got 2 digits, on and off, or 1 and 0. So then you'd go like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. What if you had 16 digits? So then it's rather different. So you could count up, you could go to 9, then you'd have another digit for 10, 11, 12. I'm just stealing actually symbols from the alphabet, but they could be anything. They could be like horse, pigeon, cow. But basically we're using A for 10, B for 11, C for 12, 13, 14, 15. and then this would represent 16. So what would this represent? Well, we've got a 15 in the 16s column, so that would be worth 15 16s, which is 240. And then we've got a 14 in the units column, so the whole thing is 254. This is 255. So this would be 256. We've got a 1 in the 256 column. Okay. So what's the best number base to use? Well, the first thing is it familiar? So base 10 is very familiar, which is very helpful. Base 2 is also pretty familiar. Quite a few people understand base 2. I used that a lot during my PhD. People who work with computers often understand base 2. Does it have a lot of divisors? It's quite nice to have a base that's got a lot of divisors. So we'll look at this. We've got 60 minutes in every hour. So 60 is a bit like a base because we count through the minutes, and then when we get to 59, we then go back to 0 and we tick on 1 hour. Same with seconds. When we get to 59 seconds, we tick on 1 minute. Seconds go back to 0. So base 60 is quite a nice base because it's got a lot of divisors. You know, you can say, or a lot of factors, like half an hour is 30 minutes, a quarter of an hour is 15 minutes, a third of an hour is 20 minutes, a tenth is 6 minutes, whereas if there was 47 minutes in an hour, it would be a nightmare, because like, what's a third of an hour? You'd have to divide 47 by 3, which, as we all know, is 15 and 2/3, but you need to use fractions. It's much more complicated. So we need lots of divisors. How long are the numbers? In binary, we get very long numbers, which uses paper. But we need to learn fewer digits. With hexadecimal, it's the other way around. We have to learn a lot of digits, but the numbers are much more short, so it's more economical in terms of space. So in binary, basically, learning the multiplication table, all we've got to learn is 1 times 1 is 1, 0 times 0 is 0, 1 times 0 is 0, and 0 times 1 is 0. I need to think about that. Anyway, we only need to learn a very simple multiplication table. Okay, here are some examples of other bases. So 60 minutes in an hour, 60 seconds in a minute, 360 degrees in a circle, and actually in astronomy, we also use minutes to measure parts of degrees. So there are 60 minutes in a degree and 60 seconds in a minute. And these are all great because they've got loads of factors, you know. If you think about 60, 2 goes in, 3 goes in, 4, 5, 6, not 7, but 10, 12, 15. Got loads of factors. 12 inches in a foot, that's got plenty of factors. 3 feet in a yard, 22 yards in a chain. Wow, 22, that's a funny one. And then 10 chains in a furlong, so we're back to decimal there. Back to base 10. Binary has a special role for computers, and also we can easily convert between binary octal, base 8, and hexadecimal, base 16. Hexadecimal is also used a lot for computers. This is how we do it. So 44 in base 10 equals 101100 in binary, basically because going from the left, the first 1 here is worth 32. Then we've got no 16s, we've got an 8 and we've got a 4. So 32 plus 8 is 40 plus 4 is 44. Now to put that into octal, what we do is we take the 3 digits on the right and we say, well, 100, that is 4. So then that's the first digit in our octal representation. Then we take the next 3 digits, 101, and that's 5. In binary, and so that's the next digit in our octal. So when we write it in octal, we write it as 54, and if we just check back, we got a 5 in the 8th column, that's worth 40, and then a 4 in the units column, that's 44, so it's working. And then to put this into hexadecimal, we take groups of 4 digits from the binary, so 1100 in binary, that is 12. In hexadecimal, that's C, because A is 10, B is 11, so C is 12. And then we take the next 2 digits, 10, that's 2. So 2 is the next digit in the hex. And again, we can see, so we've got 44 in base 10, that's 2 digits. In binary, that's 6 digits. And in hex, it's also 2 digits. But for instance, the number 100 in base 10 is only 2 digits in hexadecimal. You're going to ask me what the 2 digits are, aren't you? And I'm going to work them out live. So in the 16s column, we'll need to have a 6, because 6/16 are 96, and then we'll have a 4 in the units column. So if we're going to write, if 100 in base 10 is the same as 64 in hexadecimal. Wow, I enjoyed that. Okay, I hope you've enjoyed that. I've enjoyed that. If you have, please hit the like button. If you want to see more in the future, please hit subscribe on the notification bell, and it will let you know when we send you more. I think what's next is decimal fractions, and then after that maybe calculus. I hope you're enjoying your mathematics, and I and Chewy really look forward to seeing you next time. You can just see Chewy there, lying on the bed. He's passed out. We look forward to seeing you next time. Keep well.